Okay. Okay, we have seen force voltage analogous circuit we have drawn, and we have even applying Kichas voltage law. We have even written the okay, we have even written the differential equations. Okay, applying Kichas voltage law. Similarly, we have written we have drawn the force current analogous circuits, and applying Kichas current law, we have even written the differential equation for the electrical circuits. Okay, so for the given mechanical translational system. Okay, now let us go for the mechanical rotational system. Let us see the analogous of mechanical rotational system. Okay, so today's topic is electrical analogous of mechanical rotational system. Okay, so you know, wait, what is here? Okay, there is something wrong. System is not responding. Wait, I will just once refresh it. Now it is okay. 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 So we know that in mechanical rotational system, if I want to model the mechanical rotational system, it will have three basic elements. Okay, mechanical rotational system will have three basic elements. Number one, moment of inertia. Okay. Number two, dashpot. Other one is the spring, torsional spring. Okay, number three. So the three elements are to be considered while modeling the mechanical rotational system. Okay, so one is we must consider the three basic elements: moment of inertia, dashpot, and the spring. Okay, we will use these three basic elements of mechanical rotational system in order to determine the analogous of. Okay, so analogous of these three elements in terms of electrical system. If I want to represent these three mechanical elements in if I want to determine the analogous of these three mechanical elements, okay, in electrical terms, then I must consider three basic elements in your electrical system. Those are resistance, inductance, and capacitance. Okay. So in your mechanical translational system, the input was the force for the mechanical translational system. For electrical system, the input was the voltage or current. Okay. So when it comes to mechanical rotational system, the input is the torque. Okay. So input is the torque. So analogous to the input of the mechanical system in electrical form, analogous will be voltage source or current source. Same electrical system we are considering here. So the input for the mechanical rotational system is only one input, that is torque. Whereas for electrical system, the input can be either voltage source or it can be current source. Okay. So two types of sources are there. Okay. So if I want to represent the analogous of the mechanical system in terms of electrical, then I must consider torque voltage analogy and torque current analogy. Okay. Okay, so let us start with torque voltage analogy. Okay, so I'm considering a mechanical rotational system here, and the three basic elements are moment of inertia, friction, and elasticity. Okay, so the input is the torque. Okay, when torque is applied, what happened? The output is the displacement. Output here is the displacement. Okay, so angular displacement. When angular displacement occurs, automatically angular velocity will also occur. Okay, due to angular displacement, angular velocity will also be there. Okay, so when torque is applied, there will be angular displacement. You must consider the angular displacement as well as angular velocity. So when torque is applied, okay, So this acts as the input, and the output will be the torque due to the moment of inertia, torque due to friction, and the torque due to the sorry. This is torque due to elasticity. This is torque due to friction. Okay. So according to Newton's second law, what is it? Applied torque will be equal to the summation of the applied torque will be equal to the summation of the opposing torques. What are all the opposing torques here? One opposing torque is due to the moment of inertia. So it is represented by J into d square theta by dt square, plus another is due to the friction. Okay, another torque is due to friction, b into d theta by dt, plus another torque is due to elasticity, so k into theta. Okay, so now apply Laplace transformation to this equation. Okay, you will get Ts plus J into s square theta s plus Bs theta s plus k theta s. This you already know. Okay, so how to represent in Laplace form. Now let us consider an RLC series circuit. Okay, apply Kichas voltage law in this. Current in the circuit is I. Okay, so if you apply Kichas voltage law, V will be equal to Ri plus L into di by dt plus 1 by C integral of I dt. Okay, 1 by C integral of I dt. Okay, now take the Laplace transformation. Take the Laplace transformation for this equation. You will get, for V you will get Vs. For R is constant. For I you will get I of S. L is constant. Di by dt can be written as S into Is. 1 by C constant. Integral of I dt is I of S by S. Okay. So this is what you will get. This equation you will get. Okay. Now you just you have got two equations here. Okay. Now current can be represented in terms of charge. Okay, I equal to dq by dt, where q is the charge. Okay, so if you take the Laplace of this equation, you will get I of s equal to s into qs. Okay, so in your equation, substitute this equation. Now consider this as equation 3. Substitute this in your equation number 2. Instead of I of s, you must write s into q of s. So s into q of s. Okay, write down s into q of s, s into s square into q of s, s cancel, q of s you will get. So this is what you will get, s cancel, s square s. Okay, so arrange in the decreasing order of power of s. Okay, s square, s and some constant in term. Okay, so rearrange the terms, you will get this equation. Okay, you have got some equation here. Okay, now this equation will be similar to your equation number 1. Okay, s square into theta of s, j s square theta of s, L s square q of s. Okay, B s theta s, R s q s, K theta s, 1 by C q s. So here based on this, what is understood? T of s is analogous to V of s. Okay. T of s is analogous. What I will do is, I will go back. Why to change the slides again and again? What I will do is, I will just copy this equation. Control C. Okay. And Control V. Okay. So just to show you people, that's all, nothing else. Huh? So this is your mechanical equation. This is your electrical equation. So V of s is analogous to T of s. J is analogous to L. Theta s is analogous to Qs. B is analogous to R. K is analogous to 1 by C. So you just see in this table. Okay. T is analogous to E. You can represent voltage as E or V. Okay. So theta is analogous to Q. Okay. Theta is analogous to Q. Okay, J is analogous to L, B is analogous to R, K is analogous to 1 by C. Okay, K is analogous to 1 by C. Okay, I am deleting this. Okay. Okay. So we know that the I equal to dq by dt V equal to d theta by dt, isn't it? We know that. V is equal to angular velocity. Here omega, I have written omega, it's okay. Okay. Sometimes. So omega is equal to what? D theta by dt. I is equal to d q by dt. Okay. So when q and theta are analogous, definitely dq by dt will be analogous to d theta by dt. That is omega is analogous to I, T is analogous to V or E, B is analogous to R, J analogous to L, K is analogous to this. Newton's second law is analogous to Kichas voltage law. You can even compare the change in the level of the independent variables equations. They are also analogous to each other. Of course, we are not using this in while solving the problems, but you can compare them. Okay. So now force. I'm sorry. Wait. Why is it force? Okay. Okay. Always silly mistakes. Okay. This is torque current analogous circuit. Okay. I'm checking whether again is there any force term. No, it is not there. Okay, this is torque current analogous circuit. So I'm taking a simple mechanical system, rotational system. The applied torque here is T. Applied torque is T, angular displacement theta. The basic elements are J, K, and B. Okay, so applying Newton's second law to this basic mechanical system, I will get T equal to J d square theta by dt square plus B into d theta by dt plus K into theta. Now apply Laplace transformation to this, similar to your previous case. Okay, you will get T of s equal to J s square theta of s plus Bs theta s plus K theta s. Okay, now consider the electrical circuit. Okay. Okay, then since I have to apply Kichas current law, I will consider all the elements are connected in parallel here. Source is I, node voltage is V. Okay, this is the reference voltage. Okay, current in each element is IR, IL, and IC. Okay, so I is equal to IR plus IL plus IC. So, I is nothing but V by R. IL is 1 by L integral of V dt. IC is C dV by dt. This you already know. Okay, these terms you already know. You have learned this in your basics. Okay, now take the Laplace transform of this equation with zero initial conditions. I will become I of s. 1 by R is constant. V will become V of s. 1 by L is constant. Integral of V dt is V of s by s. C is constant. dV by dt is s into V of s. Okay, this is what you will get. Now, you know voltage is equal to the rate of change of flux linkage, isn't it? Voltage is equal to the rate of change of flux linkage. Okay, so d phi by dt. So you just take the Laplace transform of this equation. You will get Vs equal to s into d phi s. Substitute this equation 3 in your equation number 2 instead of Vs. Okay, so if you substitute, you will get Is equal to 1 by R. There was only Vs, so s into phi s. Okay, so there was okay, wherever Vs is there, you just substitute it. You just substitute Vs, s into phi s, s square phi s. You will get ss cancel here. Okay, this is what you will get. Rearrange the terms in decreasing order of s power. Okay, you will get this equation. Okay, now you can compare this equation with your equation number 1. This equation. Okay. So you can compare it. I'm writing, I will copy this equation and I will write somewhere here. Okay. I will write it here so that we can compare it. Okay. So if you observe, T of s is analogous to I of s. Okay. T is analogous to J. T is analogous to J. Theta is analogous to phi. 1 by r is analogous to b, phi is analogous to theta s, that is over, where 1 by l is analogous to k. Okay? So now you have got the mechanical and electrical terms which are analogous to each other. Okay? So let us see the table. Let us see the table. Yes. So torque is analogous to current, angular velocity is analogous to, theta is analogous to phi. Okay, so definitely angular velocity will be analogous to voltage. Okay, voltage is equal to d phi by dt, omega is equal to d theta by dt. Okay, so okay, so B is analogous to 1 by R, J is analogous to C, K is analogous to 1 by L, and Newton's second law is analogous to Kichas current law. And you know this means voltage means current transformation ratio, speed transformation ratio, we can say they are analogous to the gear values. Okay, so this is what it is. It is whatever we have discussed till now is similar to your mechanical translational system. Okay, so all things are same. Only the thing is there we used to we use the term force. Here we are using the term torque, and derivation procedure and all is same. It is very simple and easy. If anybody has any doubt, you can unmute yourself and you can ask me. Okay, strength is very low today. It's okay. Okay, anybody, if you have any doubt, you can unmute yourself and you can ask me. Okay, we will solve some problems on this. And we'll, if possible, we will conclude this topic today itself because we have solved. I am teaching you in the best way that I can. Okay, so let us solve some problems. Okay, if you see here, we have to write the differential equations governing the mechanical rotational system. Okay, so this is the mechanical rotational system. Okay, and you have to determine the differential equations, and you have to draw the torque, voltage, and torque and electrical analogous circuit, and you have to verify by writing mesh and nodal equations. Okay, so this is the given system. As soon as the system is given, you must check how many moment of inertias are there. How many are there? There are 2. So 2 moment of inertias are there means there will be 2 meshes in torque voltage analogous circuit, and there will be 2 nodes in torque current analogous circuit. That you must remember. Okay. Now initially we must write down the differential equations governing the system at each node, at J1 node and J2 node. Okay, 2 nodes are there. Okay. So 2 nodes are there. So let us draw the free body diagram at each node. So at node 1, J1. Node 1 is J1. Okay. So at J1, is there any applied torque? There is applied torque. So I can consider both sides. Applied torque is T. What will the angular displacement at J1? Let us consider it as some theta 1. 2 nodes are there, that's right. Okay. What are the opposing torques here? One torque is due to the moment of inertia itself. Another torque is due to B1. Torque is due to B1. One more torque is due to K1. Other torque is due to K1. Okay. So there are 3 opposing torques and 1 applied torque. Okay. Again, there are 3 opposing torques and 1 applied torque. I am taking this snapshot. Okay. I'll remove the video. Okay, there are 2 there are three opposing torques and one applied torque. Okay, three opposing torques are there, one applied torque is there. Angular displacement is theta 1. It is not mentioned here. So when it is not mentioned, we must assume. Okay, that's all. Okay, so wait. Okay, so there are two moment of inertia, their angular displacement. Angular velocities also, it just assume omega 1 and omega 2 are the angular velocities. Okay, so this is the free body diagram which I have drawn there in the other slide. Okay, opposing torques are J1, TJ1, TB1 and TK1. So you know the differential equations for these opposing torques. Okay, these are the differential equations. Okay, so moment of inertia proportional to acceleration, friction proportional to velocity, and elasticity proportional to the displacement. So opposing Newton, according to Newton's second law, opposing torques are equal to the applied torque. So opposing torques are what? These are the torques. So J1 d square theta 1 by dt square plus b1 d theta 1 by dt plus k1 into theta 1 minus theta 2. Why? Because k1 has two free ends. Here k1 has two free ends. So differential displacement you must consider. So let us consider the angular displacement at node 2 is theta 2. Okay, we have already considered here, so no problem. Okay, this is it. Let us consider this as equation number 1. Okay, now let us see the free body diagram at node 2. Okay, at node 2, that is J2. Okay, I will take a pen. I will draw it here. Okay, at J2. Okay, so here, is there any torque applied at J2? No torque. Torque is not there. Okay, so let us assume the angular displacement at J2 is some theta 2. Angular displacement is theta 2. Okay, if my voice is not audible, just inform anyone. Okay, so I will hold my mic nearer to my mouth and I will take the class. Okay, the angular displacement is theta 2. Okay, opposing torques are, one is due to torque. One opposing torque is due to J2. One opposing torque is due to J2. Another opposing torque is due to K1, torque due to K1. Another opposing torque is due to K2. Okay. Another opposing torque is due to B2. That's all I think. J2, K1, K2, B2. Okay. These are all the opposing torques at node 2. Okay, I will take one more. Okay, so this is a free body diagram at node 2. Okay, so applied torques are 0, opposing torques are 4 here. So summation of opposing torques will be equal to 0 according to Newton's second law. So let us go according to Newton's second law, the sum of the opposing torques. So at node 2, so this is the angular displacement at node 2, Tj2, Tb2, Tk2 and Tk1. Okay, so these are the opposing torques. So these are the differential equations. According to Newton's second law, the sum of all the opposing torques is equal to 0 here since applied torque is 0. So substitute all these equations here. J2 d square theta 2 by dt square plus B2 d theta 2 by dt plus K2 theta 2. Okay, so wait. 1 second. Slide modification. What is this doing here? Okay, J2 d square theta 2 by dt square V2 d theta 2 by dt plus K2 theta 2 plus K1 theta 2 minus theta 1. Why? Because K1 is in between J1 and J2 in this diagram. K1 is in between J1 and J2. It has two free ends. Whereas K2, B2 and B1, they don't have any free ends. Okay, that you must remember while solving the problem. Okay, you have some equation number 2. Okay, you have got some equation number 1 in terms of angular displacement. Now we know angular velocity is equal to d by dt of theta. Angular velocity is d by dt of theta, where theta is the angular displacement. So d omega by dt will be equal to d square theta by dt square. D omega by dt is equal to d square theta by dt square. Similarly, integral of omega, if you integrate on these two sides, you will get theta equal to integral of omega dt. Okay, this is what you will get. Okay, now substitute. Okay, substitute these values in the above equation number 1 and 2. Substitute this in your equation number 1 and 2. Okay, so you will get equation number 3 and equation number 4. Okay, you will get equation number 3 and equation number 4. Okay, simply substituting. Okay, if you want for your sake, okay, for your simply I can do a shortcut for your understanding. What I will do is I will just copy this. I will paste. I will move this upwards. Okay, I will paste here. Okay, so see here equation number. This is equation number 2. So if you observe this equation number 2, J2, sorry, not J square, J2. This is d omega 2 by dt square. Okay, so d square theta 2 by dt square is replaced by d omega by dt. So d omega by dt. Okay, so this is only omega. Okay, if there is only omega, you must write d theta by dt. So omega is there, d theta by dt. Okay, K2 integral of. Okay, so K2 theta 2. Theta 2 is there. Theta is integral of omega d. So theta is replaced by this. Okay, so here theta is there. Theta is replaced by this integral term. Okay, so I hope you have understood. Okay. Okay, already for mechanical translational system we have solved the problem in this way. So and I have written a lot of the terms, lot of equations I have written for each and every problem. So I think you have understood. Okay, so you just replace the angular displacement by angular velocity. That's all. You will get this equation 3 and 4. Okay, it is similar to your mechanical translational system. Now let us go for the torque voltage analogous circuit. So from the table here. Okay, from this table, so for torque voltage analogous circuit, if you remember this table, torque is analogous to voltage, angular velocity analogous to current, displacement analogous to charge and all. If you remember that, you can write down all the analogous terms. If you remember that, you can write down all the analogous terms here. Okay? Okay, and you can draw the circuit, electrical circuit. Okay, so what I will do is I will take a slide. Okay, I will insert a slide here for your sake. Okay, I am going to take this electrical circuit. Control C. Control V. Okay, this is my electrical circuit. This is only for your sake. Okay, I am taking this mechanical system and I am copying it here. Okay, so this is my mechanical system given. This is my torque voltage analogous circuit. How I have drawn? Let us see. Okay, let us see how I have drawn this. So here torque is analogous to what? Torque is analogous to voltage. Okay. Okay. Torque is analogous to voltage. Okay. So I will draw this source voltage. Okay. Next, what is there? Okay. J1. What is J1? J1 is analogous to inductor. Okay. So, okay, J1 is analogous to L1. Okay. Next, what is there? What is there? B1 is there. B1 is analogous to R1. So B1 is analogous to R1. Okay. So I will erase it. Okay. B1 is analogous to R1. Okay. Next. What is there? In between, so two nodes are there. So definitely there will be how many loops? Two loops will be there. Okay. Okay. Loop 1, two nodes are there. So there will be two loops. Loop 2. Okay. Two loops will be there. Loop 1 and loop 2 will be there. Okay. So this is my torque is analogous to voltage. You just draw the voltage source. And next J is analogous to L, B is analogous to R. Okay. If J is analogous to 1 by L, then you must connect an inductor like this. If it is 1 by L, it is not 1 by L, isn't it? It is not 1 by L. So it is in series with the source. That you must remember. When to connect in series, when to connect in parallel, you must be able to, you must have a clarity on that. Okay. Okay. So next, in between J1 and J2, what is it? K1. Okay. What is K1? It is 1 by C. Okay. In between, in J1 and J2, it is 1 by C. So in between J1 and J2, connect a capacitor. Next. Okay. Next, Amma, what is it? J2. What is J2? J2 is nothing but L2. So connect L2. Next, B2. What is B2? R2. Next, what is K2? Is 1 by C. 1 by C2. 1 by C2. So since it is 1 by C2, you have connected in series to R2 and L2. In series to R2 and L2. Okay. So if it is C2, you might have connected capacitor like this. If K2 is analogous to C2. But here it is not the case. Here K2 is analogous to 1 by C2. That's why C2 is connected in series to these two elements. That you must remember. Okay, that you must remember. If you remember that, you can, I think you can solve the problems very quickly and easily. Okay. So you must remember that. In this circuit, if anybody has any confusion in this circuit, you just tell me. You just tell me. Okay. If you have confusion, you can ask me. Unmute yourself and ask me. Okay, you just unmute yourself and ask me so that I will clarify your doubts. Okay. So I is analogous to what? Angular velocity. So I1 and I2. Angular velocity at node 1, angular velocity at node 2. Okay, they are analogous to the current. Okay. So this is what it is. Okay. So if you are able to understand how to draw this circuit, that is more than sufficient. Now what I am going to do is, I am removing this slide. Okay. This slide is, I don't want this slide. It's an additional. Okay. I'm saving it. Okay. Now you have drawn this electrical circuit. Now there are two loops. Apply Kichas voltage law. Okay. Apply Kichas voltage law. Kichas voltage law and determine the differential equation. So here source is applied voltage is E of t. Okay. Voltage drops. Voltage across each and every element. Three elements are there. So across L1 di by dt, R1 I1, 1 by C integral of I1 minus I2 of I1 minus I2 of dt should be there. So I am extraordinary person. That's why these sort of things occur. Okay. So there is no dt here. Control S. Okay. Something is wrong. Yeah. Okay. So just for dt. Okay. So these are the differential equations applying Kichas voltage law. How to write down those equations? You know that. Okay. So if you observe here, C1 is in between both the loops. That's why when you consider loop 1, Kichas voltage law equation for loop, this is the equation for loop 1. Okay. So I1 minus I2. This is the equation for loop 2. So I2 minus I1. That's all. Okay. So you have got these two equations. You just compare these two equations with your analogous mechanical rotational system equations in terms of angular velocity. These two, equation number 3 and 4. So both the equations will be similar. Equation number, what is it? Equation number 5, 6 will be similar to your equation number 3 and 4. Okay. So let us see. Okay, it's already time has crossed. Okay. Torque current analogous circuit. Okay, I will continue in the next class. Okay. If I want, I can conclude actually. Okay, I'll continue in next class. Why to delay? If anybody has any doubts, you can ask me. Okay. So you see, you must log in by, if 2 o'clock class is there, you must log in by 2 o'clock. Okay. So you are taking more than 5 minutes. Okay, to enter into the class. Okay, so if you delay, my class will be delayed and the other staff, whoever has the class, they have to suffer. Okay, so better all of you, if you log in quickly, we will start our class immediately on time. Okay, so all of you don't delay. Anybody, if you have doubts, you can ask me. Okay, as I am taking the attendance, you people